Welcome everybody to what I'm sure will be a wonderful seminar. And before I do the introductions, I would like to remind everyone that the seminar is being brought to you by a collaboration between the Atoms Group and the Laboratory of Complex Systems Engineering, led by Professor Luis Franco from University of Campinas. So the seminar will welcome Professor Achille Giacometti. Professor Giacometti got his PhD in physics from Purdue University from the United States. And today is a full professor at Foscari University of Venice. He is part of Soft Matter Group and the local director of the European Center for Living Technologies. He is also the Foscari coordinator for the Soft Comp EU network, as well as member of the management committee and group leader of WG2 from Utopia Cost Action, and one of the two coordinators of the Team Science of Complexity within the Research for Global Challenges program at Foscari. Professor Giacometti's research is focused on phase behavior of polymer and macromolecules, with emphasis on phase diagrams and of hard cylinders. Development of computational pipelines to evaluate mutations, effects in biomolecules, and general self-assembly of surfactants and other molecules in various systems. So once again, I would like to welcome Professor Giacometti, and if you're free to share your screen and start presentation. Thank you so much for being here.
So it's really a pleasure to be here with you. The spectacular picture that you see here. This is the Foscari being. I hope that you can see my mouse, right? So this is I think this is the same picture that you were showing in your slideshow, which is this is just by chance, but this is the main building of Foscari, and this is the Grand Canal. And in the case in which you are wondering, how can we do science in such a building? Well, we don't. This is where we are. This is the campus of the School of Science, which is this is Venice. This is the bridge connecting with the mainland, and this is still Venice. So we are located here, five minutes, with the bus, by Venice. So what do we do in our group? We do soft matter, as was mentioned. These are part of the ongoing effort that we are currently doing. But today I wanted to focus on two specific topics, which are these two. And in fact, I want to tell you two stories. So the first story is on liquid crystal phases that are chiral and they are tropically driven, meaning that the main driving force is simply entropy. And the other one is related to biopolymers. So the folding of a biopolymer is a self-assembly process. And this, and these two are connected as I will show you, along the way. So let me focus on the first case, and the first example. The first story is the result of the work of three talented PhD students. Hima Bindu Khalid, that was my PhD student at that time. Now she's in UK. Joy Lopez, which she was a student of Luis from University of Campinas, and I think now is still in UK. And my current PhD student Laura Dal Compare, who is currently doing a PhD on this topic. So what we are interested in is in the behavior of colloidal suspensions formed by rod-like particles, nearly more dispersed. So the dispersity here is not an issue. The typical length of these viruses are 100 of nanometers. And the typical thickness is, 10th of nanometers. So they have a significant aspect ratio. Typically, there are two examples here. The tobacco mosaic viruses, the typical aspect ratio is about 10. In the case of FT viruses, that I will discuss later on, is nearly 100. So let me focus on the tobacco mosaic viruses because this is the simplest system. And the reason is because the system is very, very stable, against the change of pH, of temperature. So essentially, the only driving force here is concentrations. And so what is happening is that by changing concentration that, I call volume fractions, so the fractions of occupied space, you start with a low concentration, you get the isotropic phases, so both the positional and orientational disorder. Then you get a transition into a phase in which you have orientational ordering. This is called the nematic phase, but still positional disorder. So the center of mass are disordered, in space. And then if you increase the concentration even further, you get what are called asymmetric phases, where you start seeing layering along one directions. And there are many symmetric phases, as I will discuss in a second. So let me show you, this is a computer representation of what I just said. So if you have a low, these are rod-like particles, at low concentration, you get a isotropic phase. You increase the concentration, you get an nematic phase. And if you increase the concentration even further, you start seeing this layering. Okay, so this is, and this has been known for decades now. And so the question is, what is the driving force, that is, promoting this changing of phases? Knowing that, as I said, the only driving force here is concentration. So the only physical quantity that matters here is entropy. And this was, shown by a long time ago, by one of my heroes, Lars von Sager, in 1949, that the phase behavior is the result of a competition between two effects. One is the rotational entropy that tend to have this the Roth's orientational disorder, and the other one is related to excluding volume, which turns out to be related to translational entropy. So, and this is very simple to understand. So imagine that you have a rod-like particle, like, you have a rod, like this one, like a cylinder. So the length is L and the thickness is R. Then if you ask, what is the excluding volume that this cylinder makes with against all the other volumes, is a volume which is proportional to R squared times L. So the square is on the minor axis. So instead of, imagine that now you have the same conformation, but in the perpendicular case. So you ask what is instead of having parallel conformation, you have a perpendicular conformation. What is the excluding volume in this case? And you see that is proportional to L squared, which is the longer axis, and R. So if you take the ratio between these two, the ratio between the excluding volume in the parallel conformations and the excluding volume in the perpendicular conformations becomes very, very small in the large aspect ratios. So essentially, the driving force is the following: that by forming a nematic phase, the system loses rotational entropy, but it gains a lot of translational entropy because of these features. And this is the driving force of this system. And so in simulations, what you do, you use what is called the spherocylinders, which is the simplest model for this. So a spherocylinder simply form, you take a rod, you take a sphere, and you roll the spheres around the segment, and you get a spherocylinders. So this model has pros and cons. In the sense that the advantage of this model is that there is a very simple rules to infer whether there is an overlapping between different spherocylinders. And this is an analytical rule, so it's very fast to check whether there is overlap or not. The drawback, the shortcoming of this model is that the prolet case, meaning that when you have aspect ratios larger than 1, is okay. I mean, this is perfectly well defined. The oplet case, when L is smaller than D, you see immediately that when L goes, is between, smaller than D, then this model degenerates into a point, is not well defined. And in fact, the original, this is the reference point for everyone who's doing simulations in the field. This famous paper by Bolhus and Frankel in 1997. So, it's been, and this was a pioneer work. And you see that they plot the concentration as a function of this aspect ratio. This is in the log scale in order to have a larger view. And you see that for the prolate case, indeed, you get isotropic nematic transition, then you get osmotic transition, and then eventually you get the crystals. This AAA is a crystals when you get at a very high concentrations. But they also did the oblate case, but for the oblate case, they actually used a different model, not this one. And this is one of the drawbacks of this case. This drawback can be solved, with a lot more work. And we did this recently thanks to the ability of Joyce, that when she was visiting my group, a couple of years ago, and by using not a spherocylinder but a real cylinders without these two hemispheric caps. And of course, the testing for overlapping, this is much more difficult, but it eventually can be done. And what you see that the nice features of this one is that can smoothly interpolate between oblate case prolate case and oblate case. So you don't have to cook up a new model for this. And as you can see, this is again, this is a packing volume fractions as a function of the aspect ratio. In this case, we don't use a logarithmic scale, but the phase diagram is essentially identical to the spherocylinders. Whereas, but in the oblate cases, so when the aspect ratio is more than 1, it's very different. And and this is the advantage of using this model. Okay, so this is I just want to make sure that you are with me. So please stop me anytime if you have questions. I enjoy questions, so I don't feel very lonely here. So, so another issue that I want to raise is the fact, both spherocylinders and cylinders are achiral molecules. There is no chirality, but in general, both the molecules and colloidal particles, they might have a chirality. And if there is a chirality, then typically what you may get is also a chiral phase. And one famous chiral phase is the cholesteric phase, in which the original the original direction. So in the original nematic phase, all the particles are aligned along a common direction, which is called the director, which is this one. But this direction gradually, rotates about an axis which is perpendicular to the original orientations, and in a helical shape. And this is called a cholesteric phase. This rotation occurs on a much larger length scale compared to the molecules. So if the molecules are nanometers in size, this typical size for this pitch is micrometers. So, and this is the reason why it can be seen in optical microscopy. So and this brings the issues of the difference between the tobacco mosaic viruses that I was referring to and the FT viruses, because they nearly have the same chemical structure. So, they are both, there is a strand here. In this case, is in the case of the tobacco mosaic viruses, is an array single strand, and there are nearly 3,000 identical proteins that are wrapped around to form an hélice. So this is clearly an helical, a chiral molecules. But it turns out that this one will form a simply purely nematic phase, whereas this one, FT virus, which has a larger aspect ratio, has a slightly different chemical properties, but nearly as the same structure, it forms a chiral nematic phase. So the issues that was raised a long time ago in this paper is what is the correlation between a microscopic chirality, so the chirality of the formic element, and the chirality of the phase. In this case, they are different. So, and as early as 1976, Strolli, using essentially the same argument that was used by Jonzager in his original paper, he speculated that this might be simply due to this again a packing. So imagine that and this is relevant. This has been shown to be relevant, for example, for packing of DNA molecules in solution. So DNA interactions. As you know, DNA is a sort of, can mimic like cylinders with analysis, rapid analysis, which is mimicking the phosphate sugar phosphates that are, wrapping around. So imagine that you have two such molecules and they come close together. If the pitch, and this is purely geometrical, so if the pitch is smaller, then they can form a larger helicoidal structure with the same hindrance. For example, if the DNA is right-handed, like bDNA is right-handed, then they form a twist with the right-handed, with the right hindrance. But if the pitch is larger than a certain amount, then the hindrance of the supercalyx will switch to a different one. And this was a speculation that was resolved. That we decided to resolve it because this was not, in spite of the fact that helical biomolecules or helical elements are ubiquitous in biological system, there were no studies on hard helices. So with Joyce, with Bingo, some time ago we decided to start such investigations. And so we used the model with a set of fused spheres, rigidly arranged in a helicoidal way, like in this one. And of course you can use a local frame orientation for this. So you have a U, which is the main axis, and W, which is the secondary axis, which is defining the azimuthal orientations. If you fix the contour length, so the length of this, and you can change the shape by changing the radius and the pitch. And you see that you get many different shapes, in this way. And I want to focus on a very slender, this is nearly rod-like, it's very slender, but it's still chiral. So we studied different shapes, the original, but now I want to focus on this because this is nearly rod-like, but still is chiral. And so what we found, this was we started, we found this in the original paper, but this is a revisitation that Laura is doing now. This is the equation of state, reduced pressure as a function of the concentrations. The original points are the black dot, and these are the other two are new result, on a larger scale. And then you see that essentially you get more or less the same sequence, isotropic, nematic, and sematic, but there are two differences compared to spherocylinders, for example. One is that this nematic phase is in fact a cholesteric phase. And I will show you this, although I call it nematic, we have evidence that this is a cholesteric phase. The second difference is that, in addition to this nematic phase, which is actually cholesteric, you get an additional phase, which is, we call it screw phase, screw nematic phase, and which is this one, which looks like a nematic phase, but has a specificity that I wanted to show you. So let me first address the case of, the issues of the cholesteric phase, we first did using density functional theory. In fact, this was shown almost simultaneous, but our group and the group by Mario Nidisca and René Varro in Utrecht. We indeed showed that, as Trolli was suggesting, that if the pitch is smaller, then you get the ends of the same, the cholesteric phase will have a rotation with the same ends as the molecules, whereas if this angle here is larger than a certain values, then you get an opposite ends. So you have a cholesteric phase on one end, on an opposite ends depends on the pitch, on this value here, which is actually related to the pitch. Then this was based on density functional theory calculations, but later on we did also numerical simulations, and we showed that this is the case. These are very difficult simulations because, as I said, locally you see a nematic phase. So on a computational box with periodic boundary condition, you don't see this. You need a special trick to do this. You know that you need a special method to pin down this this cholesteric phase. So the other so this is the so much for the cholesteric phase. The other phase that I was referring to is this we call it the screw phase, the screw nematic phase, that was actually predicted, that was shown experimentally before our study by Doji group in this paper, and they used helical flagella, which are sort of rod polymers, stiff polymers with a helical shape. And in solutions, what they found is that of course they form they have a large aspect ratio, so they form a nematic phase. But this nematic phase is special in the sense that in solution you see that this helical flagella moves up and down along the director in a screw-like motion. So it's like a screw in the cork. That's why we call it screw-like phases. And indeed, so. And the question is, what is the driving force for the onset of these screw-like phases? And this was our explanations. So imagine that you have two helices, which is in a nematic phases, which are sufficiently apart in such a way that they are free to rotate about their own axis. So they form a nematic phase because there is no region. They behave essentially like cylinders. But if they are closer, if the constituent is sufficiently light that they are closer, apart, so you see that they are locked. The secondary axis is forced to be in the same directions, and so they lose this rotational entropy about their own axis. And the only way in which they can make up for this for this loss of rotational entropy is to have a translational entropy. So they go up and down like a cork in a screw. Okay, and this is so let me show you a visual representation of this. So this is in a simulations. In these simulations, you see that they start with the layering helices. And then we label one particular layer with the magenta, darker with the magenta, color. And then you see that as the simulation goes on, this label, this fluorescent, well, they're not fluorescent label, but color coded in magenta, they go up and down. And if you focus on one specific helices, you will see that it will do exactly these helical motions. So you see that they go this magenta helix, they go up and down, and this specific helix that has been selected because it's sometimes it appears and is doing this up and down screw-like motions. Okay, so let me wrap up. So these are the take-home message is the following: that for the self-assembly, for the phase behavior of rigid helical molecules, so you get the two-phase nematic phases. One is the cholesteric phase, in which you have rotations, of the main axis in the directions perpendicular to the original orientations, and this is actually true for any. This is actually expected for any chiral molecule. So the origin of this is simply the chirality of the molecule. The second one, which we call it the screw-like nematic phase, but it is also a screw-like osmotic phase, which is associated to it, is this in this case is the secondary axis, which is rotating like a clock in the screw along the direction, the nematic directions. And this is special for helices. You don't find this special phases in any other shape. So it's special for helices. And the pitch of this nematic phase is identical to the pitch of the helices. So contrary to the pitch of the cholesteric phase, which is much larger of the size of the molecule. Okay, so when we decided, when with Bingo, this is Bingo, we said, okay, we want to do our own experiment. And so, you see that here is Bingo properly dressed to perform this very difficult experiment. So we use pasta. So imagine that, you have this rod-like part, these are called, these are a lot-like pasta, which of course they assembly in a nematic phase, but they use a different shape, kind of pasta. These are called cavatappi. They have an helical shape. Of course, they form this screw-like motion. Took like half a day to assemble this, and it was a lot of fun. So we had a lot of fun on doing this. So this is more recent work that we did with the group in Asap Whittam Cooper in Sydney. And this is again mimicking an experiment that was done by its Orimi Doji group. But I want to, in view of the time, I want to leave it aside. Laura also extended, we are currently extended this analysis to the case of helices in which part of the helices they have an attractive part, and this is this attraction, of course, derives from the induced potential which is associated to the solvent. So in the solvent. In the case of active viruses, the active viruses are highly charged, so you have to deal with charges, and Laura is also doing with this. So this is an ongoing work that we will be publishing soon. So, but now let me shift gear and go to the second topic. So the second topic is on the biopolymers. And this is the result of the work by my colleague Tatiana Skerbich, and specifically tackle this is the model that I will show you today. There are also other work that was done by Somialo Azote, and now I have there is a student, a master student, very talented master student, Tobi Arcangel, that is finishing this work. So this. So what is the idea? This is the folding of biopolymers, and of course the first biopolymer that we have in mind are proteins, and that proteins fold reversibly in water, to form a unique native state, and this is is known from the Amphisan experiment in 1970s or so, and we all know that the driving force of this is what is called the hydrophobic effect. So the fact that the polymer try to squeeze out water in order to avoid unfavorable contact. This is is well known, and essentially although it's very different from a standard polymer, it behaves like a standard polymer in a poor solvent, if you want. So and then you can use the theory that people did for starting from Fleury in studying conventional synthetic polymers. So the typical thing that you do is you trace out the microscopic degrees of freedoms, which are here represented by the small r coordinate. So you trace out, you integrate over this to get an effective potential, which is called the mean force potential, which only depends on the larger degrees of freedom, which are capital R, which are the degrees of freedom of the polymers, of the biopolymers in this case. So this is the typical things that you do in polymers, and this is and then you can build on 50 years or later on polymer theory that started with the Fleury in the 50s, and they all use the class of string beads models, and there are many of them. This particular one is called the tangent bead model. But they all in spite of the minor difference, they all have three essential ingredients. One is connectivity, so something preserving the connectivity between different beads, which is mimicking the presence of covalent bonds. The second one is excluding volume, meaning that two monomers cannot overlap for folding. And the third one is the presence of a short-range attraction, which is mimicking this hydrophobic effect, the effect of the solvent. Okay, so again, in spite of the difference, of the model, the phase diagram of the system is more or less the same. Yes, a high temperature. At high temperature, this is the temperature axis. At high temperature, you have an extended phase where the polymer is extended, and this is also called the Fleury regime. At low temperature, you have a collapse phase, a very, which can be either a very dense globule or a crystals. And in between, there is a specific transition temperature, which is called the theta temperature, where you have a transition. And actually, in this case, the chain behaves like an ideal chain, so with no excluded volume. So this is the phase diagram. So if you now cool down, you ask, what is the ground phase? The ground state of this one system only depends on one parameter. So this is the, what happens at the ground state below the folded temperature. So and the only parameter is this range of attractions. So if the range of attractions in unit of sigma is the diameter of the beads, so if the range of attraction is smaller than the sigma, then there is no way in which the different parts of the polymers can attract. So you get a coil. Whereas as soon as this is above this one, is above this values, above this one, then this will form a global, either a global or a crystal. It depends on the regime. So this is in this particular case, you get you need just one parameter, which is one axis, which is this range of interaction to describe the phase behavior of these polymers. So what is the difference between a polymers and a biopolymers, such as the proteins? Well, it's very different in the sense that, in the case of polymers, as I said, you start with if you have a high temperature, so you have high energy, you have the system is open, but and you have a huge number of microstates. So there is not only one possible state, microstate, but there are many. And then when you cool down, you get a global, but the global is highly degenerate. There is not a unique global, but there is a huge different conformations of global that that of course they are equivalent in the sense that they are local minima, metastable minima, and then you can go from one to another one by thermal fluctuations. So in this case, you start with a highly degenerate system at high energy, and you get a highly degenerate system at low energies. In the case of polymer, this is very different. In the case of polymers, again, at high energy or at high temperature, you get a coil, you get many states, but as you cool down, the energy decreases, but also the entropy decreases. So there is some sort of bias potentials which drive the system towards a unique native state. So this is the crucial difference with the standard polymers. So, and the question is, there is an open question, see what is this driving force, but that is still open. But let's forget about these issues. The question is, okay, if you wanted to describe not a standard polymer, but a biopolymer like this one, you need to change the model. So, and the important message that these figures show you is that you need to reduce the conformational entropy. Okay, so because you need to reduce the possibility of having this highly degenerate state. So, and what is the conformational entropy? So imagine that you have a polymers, and these are these beads needs to be as long as the bead is attached to the rest of the polymer, can achieve any position in space. And in fact, there is a spherical symmetry. Okay, and so imagine that now so in this case, this is a tangent bead in the sense that the monomer and monomer distance is exactly identical to the diameter of the system. So that's why they are tangent. Imagine that now that you are allowing a partial interpretation between consecutive beads. And you see that what is happening is that then this additional beads is restricted. So the flexibility the freedom of rotating, this is reduced. So this angle is smaller than the previous one. And the more you increase this overlapping, the more you have a restriction. So in this respect, you have a decrease of this conformational entropy, which is translating to some sort of effective stiffness, whose origin is entropic one. So is due to the excluded volume. So the first thing that you can do in order to reduce conformational entropy is, as I said, that you allow the partial overlapping between consecutive bonds. So this ratio that originally was 1, decreases. And the more it decreases, you see that the more you have less flexibility in the polymer. In this respect, you have what you do is actually you are breaking one symmetry. You are breaking the spherical symmetry, the original spherical symmetry of the tangent bit, in favor of a cylindrical symmetry, which actually respected the connectivity of the polymer. So this is more natural, a more natural system, symmetry for the polymer. So in this way, you have one more parameter to with respect to the original one that you have to deal with in the ground state. But you can do more. You can further reduce the conformational entropy, but adding a side sphere that can have a purely entropic region that can have different sizes. You see that by going in these directions, you increase the size of the side spheres, and even here you break an additional symmetry. Instead of having cylindrical symmetry, you have a biaxial symmetry. So you go from you reduce the symmetry even further. And so now we have a second parameter that you can deal with, and then in addition to the third parameter that was the range of interactions, this will describe the whole ground state. So the whole ground state of the system must depend on these three parameters, and we can study this systematically, this ground state, and this is what we did. So our model, in fact, has three parameters, and it turns out that is relevant for proteins because if you put typically numbers, this side sphere is located along one specific direction, which is turns out to be the one of the of the side sphere or the side chains in real proteins. So this is physically motivated in this respect. In fact, we tested this, and I don't want to. I just wanted to show you, to treat this as from the statistical mechanics point of view. So as I said, we have three parameters, so we can study the ground state. So when we cool down below the folding temperature, we can study the shape of the phase, the particular phase. And this is of course, you have three planes that you have to study. This is one of the three in which we have a local interpretation on the x-axis, on the y-axis, the size of the side spheres. So if you have a small side spheres, then you get a global, like a standard polymer. If you have a very high side spheres, so you get a coil because the polymer cannot bend because of this of steric hindrance. And in between, you see that you have a huge regions, and then if you study these regions, it turns out that in this you have a region in which when you cool down, you find an helix, because an helix is a very natural way to packing these side spheres. And then you find there is a region also you find beta-like strata, like planar shears, planar sheets, in which the side spheres are located either in the top or in the bottom, like hexagonal packing. And then there is also a double helix, and then you see that there is in between there is a point where these three phases, the helix and the beta and the global, they meet. And this is some sort of a triple point. Actually, it turns out that it's not a triple point, is a regions. And in these regions, what is happening is that it turns out that they have you observe combinations of these two typical secondary structural elements in proteins. So a combination of alpha and beta, and this is point one, and point two. They all nearly have the same energies. So there is a degeneracy in this phase, which is this extended triple phase that we call it elixir because it has these special properties, in the sense that all the shapes, irrespective of the particular, it can be either a combination of alpha and beta, or alpha or beta, but they all have the same energy, apart from a finite size effect. So there is a degeneracy in terms of an energy. So let me show you what is happening. So let me wrap up and let me show you what is happening. So this is the phase diagram that I was showing you before. You take a point here, which is an hélice. You start with a high temperature. You cool it down. You measure the specific heat, which is a signature when you have this transition which is a second order phase transition, from a colloidal to an helix, and you get a specific helix with a specific shape. In general, this is unrelated to to what you find in proteins. Then you take another point in the beta phase, then you cool it down, then you get again at the typical temperature, you get a peak in the specific heat, you get this beta-like sheet. Again, with a specific shape, which is in general unrelated to the real proteins. And what I want to stress here is that there is a one-to-one correspondence between the state point that the particular set of parameters that you take, for example, and the shape of the helix. So if you take, for example, a different point here, you get a different, still an helix, but with a different shape. If you take a different point here, you still get still a beta, but with different shape. If you take a point here, you get two differences. The first difference is that you have multiple transitions. So you have intermediate transition, and then you get the final transitions. The second difference is that you get a ground state, which is a combination of this, and this ground state is not unique. If you do this, again you get a different. In general, you get a different shape with the same energy. So there is a highly degenerate. So let me show you a visual representation of this. So this is a point in the case of the helix. You start with high temperature, you cool it down, as you get an helixes. So this is an annealing Monte Carlo simulation. Again, this is you take a point here, you get a beta, where you have this typical hexagonal lattice for the side spheres. If you take a point here, in this particular case, you get this particular shape. But if you repeat with the same state point, you get in general another. In this particular case, you get you see they have two betas like structure and an helixes in between. But if you repeat the thing, you get a different shape. So and this is the typical a sort of visual representation of some of the different shapes that you find in these regions. And the very nice things of this is that as I said, that they are nearly degenerate in energy. So it means that you start with if you start the simulations with this one, and then you do just a little kick like thermal fluctuations, then you get another one of the other shape. Then you do another kick by thermal fluctuation, you get another shape, and so on. So essentially, this behaves like a sort of nanomachines that they can change shape with with thermal fluctuations with no energy barriers. And I found this I found this very nice. So and my colleague Tatiana Skrbich is refining this model. She has many new results, but I wanted to end with a different perspective in this self-assembly. So imagine now we take some of these molecules, that I was showing before, where we know exactly what is happening in the ground state, and we put in the box. And of course, if we put in the box and we run simulations, so in the solutions, effectively this is like a solutions, at low concentrations, you expect that every particles behave as they were, as on its own, so it folds like an isolated polymer. But above a certain concentrations that we measure to be 10 millimolar, then something happens. And of course, what happens, it depends on the temperature. So if these are three simulations that are thermalized at different temperatures in these reduced units. So this is high temperature, this is intermediate temperature, and this is low temperatures. Well, low temperature, and you see that at low temperature, it's clearly that you have a tendency to aggregate more, and this aggregation process, is independent of the original shape of the polymers. And you can, of course, this is simply a visual representation, but you can get a more quantitative representation of this if you measure the energy. So this is the total potential energy, and you can divide this between the intra potential energy, so the energy within between monomers within the same polymers, and inter potential energy, which is between monomers of different belonging to different polymers. And then you see that at high temperature, the black curve is here, is flat, is completely zero. So the total potential energy essentially corresponds to the total intra energy. At intermediate temperature, you start seeing something, but at the low temperature, you see that there is a significant fraction of this that goes into the inter potential energy. And of course, if you cool this down even further, but simulation become very, very demanding in this case, then you expect that this will increase even further. So in this respect, this is a process that can mimic. So we also have Tobias is doing a slightly different model, which is a polymer with bending rigidity rather than entropic stiffness. This had the advantage is that the ground state is well known. There are just two ground states. One is a rod-like structure and the other one is a toroid. So we know exactly what is happening at low temperature for a single one instead of having a degeneracy. But it turns out that this is relevant, for example, for amyloid formations, because what is believed but is not shown is that in this analogy between proteins and a liquid system, the native states correspond to a gas phase where each protein folds individually. The amyloid phase corresponds to a crystal phase when we have this highly concentrated stacking, and there is something in between which is the analog of a liquid. So with this model, of course, this is what the predictions, but there is based on experimental result, but there is no confirmation of this. And what we hope is that using this model, we could shed some light on this problem, which I think is fascinating. So I think it's time to wrap up because my time is actually up, and I want to leave time for the questions. So as I mentioned, I told you two stories. One is related to the onset of these chiral phases on the assembly of rigid helices, and we saw that there were two phases. One is the cholesteric phase, whose origin is simply the chirality of the molecule, and the other one is the screw-like phases that they stem from the specific shape of the helical particle. And the second story that I told you was this symmetric breaking in biopolymers. So the idea is that as you decrease the symmetry by breaking this successive symmetry, you get new phases. You get this marginally stable phase which are between the original phases. And with this, let me thank I have to thank many people because the Foscari team that I will show you in a second. In the liquid crystal, I collaborated for the liquid crystal problem. I collaborated with all these people, and with the for the polymer case, I collaborated. I enjoy this collaboration with all these people. And I leave you with a picture of the Foscari team. So this is Laura, and this is Tatiana that I was referring to before. And with this, I thank you for your attention, and happy to take questions.
you.